Hello everyone and welcome to another IB Physics video. Today we'll be doing paper 1 questions from May 2021, Timezone 1. So let's get started. In this first question, it says two sets of data shown below with circles and squares are obtained in two experiments. The size of the error bars is the same for all points. So you can see there's one of the experiments in circles and the other experiments in squares. And the question then says, what is correct about the absolute uncertainty and the fractional uncertainty of the y-intercept of the two lines of best fit? So number one, since we're doing lines of best fit, I'm gonna draw the line 6. So, and you should go through the upper and lower bounds of the uncertainty for the first and last points. We're going to do the same thing for the squares. So let's do something like that. Something like that. And immediately you can see that if you're looking at the y-intercepts, the uncertainty is going to be approximately 1 for both the blue and the red maximum minimum slopes. So if you look at the first part, the absolute uncertainty is almost the same for both. Now, what about the fractional uncertainty? If you try to do the fractional uncertainty, well, it's going to be, let's say for the circles, it's about uncertainty of 1 over the value of 3. So about 33%. If you do it for the squares, it's plus or minus 1 over 1, which is about 100%, which means the fractional uncertainty for the squares is a lot larger. And the answer is D. In question number 2, it says a large stone is dropped from a tall building. What is correct about the speed of the stone after 1 second? And you have 4 options. The speed is decreasing or increasing. And then it's either decreasing at an increasing rate or at a decreasing rate. So here's the thing. We're talking about the speed here. And of course, because of gravity, the speed is going to change. Acceleration is the rate of change of velocity. So as it falls, of course, it's going to go faster and faster. It must mean that the speed is increasing. But what is happening to the acceleration? Well, it doesn't say we should ignore the effects of air resistance. So we're going to have the force of gravity downwards, but we also have the force of drag upwards. And as it goes faster and faster, the force of drag from the air increases, which makes the acceleration decrease. So as it goes faster and faster, it does still go faster and faster, but the acceleration decreasing means it's a decreasing rate. This rate it's talking about is the acceleration. So the answer is D. Question number 3. The graph shows how the position of an object varies with time in the interval from 0 to 3 seconds. At which interval does the instantaneous speed of the object equal its average speed over the interval of 0 to 3 seconds? So if you take a ruler and you want to get the average speed, you just draw a line from the beginning to the end. That would be the average speed. And if you want to get instantaneous speed, you have to get the tangent. So you'll take this, and if you have a ruler, you can just move it around. So at A, it's not tangent. At B, it is not tangent. At C, it is approximately tangent. So the answer must be C. In question number 4, it says it takes a car 20 minutes to climb a hill at constant speed. The mass of the car is 1,200 kilograms. And the car gains gravitational potential energy at a rate of 6.0 kilowatts. The question asked then, take the acceleration of the gravity to be 10 meters per second squared. What is the height of the hill? First, let's look at this expression here. This is the rate of change of gravitational potential energy, which would be the change in gravitational potential energy. And it says rate, so it's divided by the change in time. So what is the change in gravitational potential energy? The mass times the gravitational acceleration times the height. And the change in time is just the change in time. And this has to equal to 6,000 watts. So let's input the numbers. 1,200 kilograms times 10 meters per second squared for the gravitational acceleration times the height divided by. And the amount of time it takes is 20 minutes, so it's 20 minutes times 60 seconds for every minute. It wants you to find the height, so the height will be 6,000 over 1,200 multiplied by 20 multiplied by 60. And 20 times 60 is 1,200. So the answer would be 6,000 divided by 10, which is gravitational acceleration. The answer is C, 600 meters. In question number 5, it says the mass is released from the top of a smooth ramp of height h. After leaving the ramp, the mass slides on a rough horizontal surface. The mass comes to rest at a distance of d. What is the coefficient of dynamic friction between the mass and the horizontal surface? If we look at the changes of energy, as it goes down, the gravitational potential energy decreases and it becomes kinetic energy. And when it reaches this rough patch, the kinetic energy decreases and it's removed by frictional forces. So there's a friction loss. So the gravitational potential energy, of course, is mgh. And we're going to skip the kinetic energy because it goes all the way to 0 at the end anyways. And the friction loss will be the force of friction times the distance, which is the definition of work. The force of friction can be found using the friction coefficient times its normal force. In this case, mass times the gravitational acceleration. And the amount of energy lost to friction should equal to the gravitational potential energy, mgh. Simplifying this, mass and gravitational acceleration cancel out. The frictional coefficient would be simply the height divided by the distance. The answer should be D. In the next question, question number 6, masses x and y rest on a smooth horizontal surface and are connected by a massless spring. The mass of x is 3 kilograms, so let's write that down. And the mass of y is 6 kilograms. The masses are pushed toward each other until the elastic potential energy stored in the spring is 1 joule. The masses are then released. What is the maximum speed reached by mass y? So there's two things we have to do. Number one, the total kinetic energy has to be 1 joule. Second, we have to follow the conservation of momentum so that the final momentum is equal to the initial momentum. But the initial momentum is 0 because both of these masses are at rest at the very beginning. So how do you find the final velocity of y then? Okay, number one, if you apply the conservation of momentum, what we have is the momentum of mass x, which is 3 times the velocity of x, has to equal to the momentum of mass y, which is going to be 6 times the velocity of mass y. And we're only going to look at the magnitudes, not the directions, so that they're equal and opposite. Okay. That means the ratio of the velocity of x to the velocity of y is going to be just 2. This basically means mass X moves twice as fast because it has half the mass. If we do the same for the ratio of the kinetic energies, we're going to get 1/2 the mass of y, mass of x, and the velocity of x squared over 1/2 the mass of y times the velocity of y squared. Now, the 1/2s cancel out. The ratio of the masses, of course, the mass of y is twice as big, it would be 1/2. We know the ratio of the velocities, which is going to be just 2, and they're squared, so you square this. And that means you're going to have a ratio of the kinetic energy is also equal to 2, which means object X has twice the kinetic energy as y. Because of this ratio, we know that X has 2/3 of the kinetic energy, and y has 1/3 of the total kinetic energy. Because if you add 2/3 and 1/3, of course you get the whole. Okay, so let's try the kinetic energy of y is equal to 1/3 joules because the total is 1. And this must equal to 1/2 the velocity, the mass of y times the velocity squared of y, which is the equation for the kinetic energy. The velocity of y is the square root. The mass is 6, so it's 1/3 divided by 6 times 2 because of this 1/2, which is the square root of 1/9, which is 1/3. The answer should be B. Question number 7. It says a force acts on an object of mass 40 kilograms. The graph shows how the acceleration of A of the object varies with its displacement d. The question asks then, what is the work done by the force on the object? Well, in order to find the work, we will have to find the area of the force displacement graph. Now, this is an acceleration displacement graph, which means we have to convert acceleration to force. Fortunately, F equals ma. All we have to do is you have to multiply these numbers by 40 to get the force. So 20 times 40 is 800 newtons, and 10 times 40 is 400 newtons. Now we have to find the area. And we can find the area very easily. Let's just divide it into two geometric shapes. The first is going to be just this rectangle. And the area of this rectangle is going to be 400 newtons times 4 meters. And then we have the area of this triangle here. The area would be 1/2. The base is 2 meters. And the height is 400 newtons as well, which is just 400. So 400 plus 4 is 1600. Adding 400 plus 1600 would be B, 2000 joules. Question number 8. Which aspect of thermal physics is best explained by the molecular kinetic theory? If we recall, the molecular kinetic theory describes how pressure is affected by volume and temperature. And of course, this is where we get the equations for the ideal gases PV equals nRT. So, literally, the answer should be A. The equations of the state of ideal gases is best explained by this model here. What about the other ones? The difference between Celsius and Kelvins is not described by this model. It does not give us the value of the Avogadro's number, and it doesn't prove the existence of gaseous isotopes. On question number 9, it says when 40 kilojoules of energy is transferred to a quantity of a liquid substance, its temperature increases by 20 Kelvin. When 600 kilojoules of energy is transferred to the same quantity of liquid at its boiling temperature, it vaporizes completely at constant temperature. And then it's asked what's the ratio of the specific latent heat of vaporization to the specific heat capacity of the liquid. So we're going to start off with writing down both equations. Here for the specific capacity, we know that the heat transferred for the specific capacity is going to be the mass times heat capacity times the change in the temperature. Likewise, heat transfer for the change in phase from liquid to a gas will be equal to the mass times the latent heat of vaporization here. So we need latent heat of vaporization, which is the amount of heat you transferred divided by the mass. You have to divide this by the specific capacity. And according to this equation, would be the heat transferred per mass per change in temperature. Now, we can simplify this by canceling out the masses. It will simply become heat transferred to change the liquid into a gas divided by heat transfer to change the temperature, and then multiplied by the change in temperature. In this case, that would be 600 kilojoules divided by the 40 kilojoules and multiplied by 20 degrees Kelvin. Doing so, well, you get 15 times 20, which would be 300, and the units are just Kelvin. The answer should be D. For this next question, question number 10, it says two ideal gases X and Y are at the same temperature. The mass of the particle of gas X is larger than the mass of the particle of gas Y, which is correct about the average kinetic energy and the average speed of the particles in gases X and Y. First, they have the same temperature, which means that they will have exactly the same average kinetic energy. Second, it also says that the particle of gas X is larger. And having the same kinetic energy, if you have a larger mass, it means the speed is going to be lower. So Y has a larger speed. That means the answer should be B. Question number 11. An object performs simple harmonic motion. The graph shows how the velocity v of the object varies with time t. The displacement of the object is x and the acceleration is a. What is the variation of x with t and the variation of a with t? So you have a set of graphs you have to kind of see down here. So you have 4 graphs. So let's study what happens in the velocity graph first. If you look at the velocity graph, well, if you want to find the acceleration is the change in velocity over the change in time, which means the slope is going to be the acceleration. The initial slope is 0, so it starts with 0 acceleration. And immediately it falls down, so here you have a negative slope, which means it has a negative acceleration. Okay, what about the displacement? Well, if it has a positive value for the velocity, it means it will have a positive slope. And then it will proceed to go to 0. So here the velocity is 0. So the slope for the displacement should also be 0. So let's look at the possible answers then. we said acceleration should start at 0 and then become negative, so A is a possibility. In B, it does start at 0, but it then goes to the positive side, so it cannot be B. For C, it starts at 0, and acceleration goes to the negative side, so it could be possibly C. It cannot be D because the acceleration does not start at 0. Now let's look at the slopes for the displacement. We want something that starts with a positive slope. So if we look at the first A, the slope is indeed positive, and it goes to 0. What about C? Here, the slope of the displacement starts at 0 slope, which means it has 0 velocity. This cannot be one of the answers, therefore the answer must be A. For the next question, question number 12, it says a sound wave has a frequency of 1 kilohertz and a wavelength of 0.33 meters. What is the distance traveled by the wave in 2 milliseconds and the nature of the wave? Let's start off by looking at the nature of the wave. It's a sound wave, so therefore it has to be longitudinal. Second, we want to find the distance traveled. And the way you get the distance traveled is you simply get the velocity times the amount of time required. Now, if you want to find the velocity of the wave, of course, the velocity of the wave is simply the frequency times the wavelength. And all we have to do now is you have to input the numbers. The frequency is 1,000 hertz, which is 10 to the power 3. The wavelength is 0.33. And the time required is 2 milliseconds, which is 2 times 10 to the negative 3 seconds. This term and this term here cancel out, and you're left with 0.33 multiplied by 2, which is 0.66 meters. The answer should be C. Number 13. Monochromatic light of wavelength lambda is incident on a double slit. The resulting interference pattern is observed on a screen at a distance of y from the slits. The distance between consecutive fringes in the pattern is 55 millimeters when the slit separation is A. Lambda, y, and A are all doubled. What is the new distance between consecutive fringes? So first of all, let's start off by writing down the equation for double slit interference, which would be just d sine theta is equal to n lambda. Next, some of the variables have been changed. Usually we use d for the separation between the slits, but in this case they are asking for a, so let's change that to a. Second, it's just a separation from the slits, and it's going to be equal to the distance between the central maximum n equals 0 and the first constructive interference point, which is n equals 1. So let's just use n equals 1 here, which means we just left with lambda. Next, the problem does not specify an angle, but if you think of this as a triangle, the distance between the slits and the wall is y, and separation between the fringes, let's call this S. So sine theta will be approximately S over y. This is a small angle approximation. And we can use S divided by y here. Finally, let's simplify this. We have fringe spacing is equal to lambda divided by the separation between the slits multiplied by the distance y. And what we have here is all of them multiplied by 2. So 2 times the wavelength, 2 times the separation, and 2 times the distance. 2 times 2 divided by 2 is simply 2. So whatever the fringe spacing was before is just multiplied by 2. In this case, 55 times 2 is 110. Next question, number 14, says a metal rod of length 45 centimeters is clamped at its midpoint. The speed of sound in the metal is 1,500 meters per second, and the speed of sound in air is 300 meters per second. The metal rod vibrates at its first harmonic, and the question asks, what is the wavelength in air of the sound wave produced by the metal rod? So first, if we think of the metal rod as this blue line here, and it's in its first harmonic, number one, it's clamped at its midpoint, so the midpoint must have a node. So the first harmonic will look something like this. And there is exactly 1/2 of the wavelength inside of this rod of length L. Next, what we have to do now is, of course, wavelength is going to be 2L, and the frequency will be the velocity divided by the wavelength, so it's the velocity over 2L. And this is the frequency in the rod. What about the frequency in the air? Well, the frequency in the air is going to be exactly the same. So it's exactly the same as the frequency in the rod, which again is the velocity over 2L. But if we know that there's also another equation for the frequency in the air, which is just the velocity in the air divided by the wavelength in the air. So now we have the velocity of the wave in the rod over 2L is equal to the velocity in the air over the wavelength in the air. And it asks us for the wavelength in the air. So that is equal to the velocity in the air divided by the velocity in the rod multiplied by 2 times the length. All we have to do now is input the numbers. The velocity in the air is 300. The velocity of sound in the rod is 1,500. 300 over 1,500 is simply 1/5. And the length in the rod is 45 centimeters. Times 2 would be 90. And finally, 90 divided by 5 would be 18. The answer should be C. In this next question, number 15, it says 2 charges Q1 and Q2, each equal to 2 nanocoulombs, are separated by a distance of 3 meters in the vacuum. What is the electric force on Q2 and the electric field due to Q1 at the position of Q2? So let's start off by writing down the equations for electric force and electric field. Electric force would be equal to the Coulomb constant times Q1 times Q2 divided by the distance squared. Likewise, the electric field is the Coulomb constant. In this case, only multiply by one of the charges, Q1, divided by the distance squared. You have access to the physics booklets during the test, and this is a multiple choice question, so you don't have access to a calculator. So you have to estimate. The Coulomb constant is 8.99 times 10 to the negative 9, but you can just say it's 9. So you round up, times 10 to the power of negative 9. Q1 is 2 times 10 to the power of negative 9 for nano. And again, the second charge, 2 times 10 to the power of negative 9. And you divide by 3 squared, which is just 9. So the 9's cancel out. We have the Coulomb constant actually is 10 to the power positive 9. So this and this cancel, and you're left with 10 to the negative 9 times 4. So this is the force on Q2. Now notice, the electric field is almost exactly the same equation, except it is missing one of the other charges. So if we remove this charge here, you would have the electric field. And this means it's just 2 without any exponents for the power of 10, and that would be 2 times 2 newtons per coulomb. The answer should be A. In question number 16, the question reads, two conductors S and T have the voltage and current characteristics graphs as shown below. So in this graph, you have the current in the y-axis and the voltage in the x-axis. When the conductors are placed in the circuit below, the reading of the ammeter is 6 amperes. What is the EMF of the cell? So notice first, these are resistors in parallel configuration. And we have two statements about the current and the voltages of these two resistors. First one, because they're in parallel, the voltage drop through S will be equal to the voltage drop through T. They have the same voltage drops. Number two, the total current is equal to the current through resistor S plus the current through the resistor T. So the currents add up. Now, if we look at the graph here, they both have the same voltage. So I'm going to draw a vertical line. And whatever the intersections are will give us the individual currents of both. And they should add up to 6. So if you're at 1 volt, the sum would be around 1 ampere, so it's not what we need. So let's move a little bit to the right. Increase the voltage to 2 volts. And if you increase the voltage to 2 volts, the sum would be something less than 1, plus 1.5, something around 2 point something amperes, which is still too low. And you can continue going to the right. And if you reach 4 volts, notice that both of them will have a current of 3. If you have a current of 3 through both S and T, they will add up to 6 amperes of current, which means you do need 4 volts to get 6 amperes. Question number 17. For a real cell in a circuit, the terminal potential difference is at its closest to the EMF when A, the internal resistance is much smaller than the load resistance, B, a large current flows in the circuit, C, the cell is not completely discharged, or D, the cell is being recharged. So first of all, the terminal voltage is equal to the EMF minus the current times internal resistance. Simply because this is how much the voltage drops because of the internal resistance. Now, if you want the terminal voltage to be close to the EMF, you want this other term here to be as close to 0 as possible. And to do that, either you have to have very low current or a very low internal resistance. So this would be the case for A, where the internal resistance is much smaller than the low resistance. It means this is as small as possible. A large flow would have the opposite effect, and the cell being discharged or recharged does not have any effect on this terminal voltage either. Number 18, an electron enters a space inside a current-carrying solenoid. The velocity of the electron is parallel to the solenoid's axis. What is the electron doing? Is it slowing down, speeding up? Is it undeflected, or is it deflected outwards? So first of all, a solenoid creates a magnetic field. So if you have a solenoid, which is a wire that looks kind of like this, it would create a magnetic field that it goes to the right or to the left. So let's assume for 1 second that it goes to the right. The electron moving through the axis would mean the electron is either moving in this direction or in this direction. It's going to go straight through. Now, in order to have a magnetic force, the velocity has to be perpendicular to the magnetic field. In this case, the magnetic force will be 0, which means C, the electron will be undeflected. Another way you can think about this is, well, they did not actually specify the direction of the magnetic field and did not specify the actual direction of the electron relative to the magnetic field. You just know they're parallel. And this means even if you were able to change the velocity, you will not be able to tell if it's slowing down or speeding up. So logically, you can eliminate this ones. Same way, you will not be able to tell if it would be deflected. So the answer must be C. Question number 19. A child stands on a horizontal rotating platform that is moving at a constant angular speed. This centripetal force on the child is provided by A, either the gravity, B, the friction, C, the tension in the child's muscles, or D, the normal reaction force. So if you were to draw this platform here, like so, and let's draw a representation of a child here. We know that the centripetal force has to be going towards the center of the horizontal circular path. So you need a force in this direction. Now, the force of gravity is downwards. So this force of gravity will not be able to give you the centripetal force. It's in the wrong direction. So let's go like that. Gravitational force is incorrect. The normal reaction force will be upwards. For the same reason, you need a force towards the center of the circular path, so it would not be able to be provided by the normal reaction force. D is also incorrect. Now, the tension in child's muscles, just because you tension your muscles doesn't mean you will be yeeted in a certain direction, so it's not the answer either. The only force that would be, that could possibly be towards the center in this case is a friction force, B. One other way to logically reach this conclusion is if you think about, if you pour oil on the child's feet, he'd probably slide off the circle anyways. It must have been the friction that allowed the child to stay in the circular path. Number 20. A simple model of an atom has 3 energy levels. The differences between adjacent energy levels are shown below. And the question asks, what are the 2 smallest frequencies in the emission spectrum of this atom? If you want the 2 smallest frequencies, you need the 2 smallest energy differences. And the smallest energy difference would be going from this level down to here. Let's call this E1. The second smallest energy level would be from this level down to here. Let's call this E2. And the largest change in energy will go from the top one to the bottom one. I'm not going to label this because we don't need this one here. Now, if you want to find the frequencies, the energy will be equal to the Planck constant times the frequency. So, Planck constant times the frequency 2. And in this case, the Planck constant is 6.63 times 10 to the power of negative 34. Notice you're not supposed to be able to need a calculator for this question, so the numbers provided very easily cancel out. So if you get 6.63 times 10 to the negative 19 and you divide by the Planck's constant, you would get just 1 times 10 to the 15 hertz. It's not equal, so I'm not going to use the equal sign. Likewise, 13.3 is 2 times 6.6. So this is also going to be 2 times 10 to the 15 hertz. So the answer should be C. Number 21. What is the relation between the value of the unified atomic mass unit in grams and the value of Avogadro's number in moles? So we have 4 options. They can have a ratio of 1. They can multiply and have a product of 1. They can add and have a sub of 1. Or they can have a difference of 0. Now, just by looking at the actual values, 1 atomic mass unit, according to the physics booklet, is 1.661 times 10 to the negative 27 kilograms. If you were to change it to grams, it would be 10 times 10 to the negative 24 grams. And Avogadro's number, or Avogadro's constant, is 6.02 times 10 to the 23. Immediately, a ratio means division, right? If you divide them and have a ratio of 1, that means they're equal, and they're not equal. The ratio cannot be 1. If you add them, their sum is not going to be 1 either. If you subtract them, the only way to get 0 is if they're equal. Again, they're not equal, so you cannot have a difference of 0. That must mean the product is 1. And if you actually try it, multiplying this times this does indeed give you a value of 1. Number 22. In a hydrogen atom, the sum of the masses of a proton and the electron is larger than the mass of an atom. Which interaction is mainly responsible for this difference? Well, in chapter 7, you have learned about binding energies, which is caused by the missing mass. And the reason there's mass missing in the nucleus is because energy is released during fusion. But in this case, a proton does not have any other nucleons, so it cannot be the binding energy. Of course, the nucleus releases energy during fusion because of the strong nuclear force, which means it cannot be the strong nuclear force that causes a change in mass. It's not a gravitational force, it's not a weak nuclear force. Because it's the interaction of a proton and an electron, it has to be an electromagnetic interaction. Now, another way to interpret this is when you have a proton without an electron and you add the electron, adding the electron makes the energy of the electron go down. Recall all the energy levels of the electrons in hydrogen have negative values, so it releases energy when the electron is put into the orbit. The energy is released, mass is energy, according to Einstein's E equals mc squared. So the mass should be very slightly lower and equal to the amount of energy released when the electron was put into orbit. Number 23. Which Feynman diagram describes the annihilation of an electron and its antiparticle? First, notice that time flows towards the right. And let's look at A. This arrow does not mean it's moving to the right. This arrow means if it's the same direction as time, it's the regular particle. This other arrow in the opposite direction of time, it means it's an antiparticle. And when they meet, they destroy each other, so they don't exist afterwards, and you have a photon. The answer is A. Let's look at why B, C, and D are not these answers. For B, this is a regular particle, and this is also a regular particle, so it's not the right answer. Another requirement for Feynman diagrams is for every interaction or every vertex, there should be one arrow going in and one arrow going out. This does not meet that criteria, so it cannot be B. For C, same thing. Every interaction should have one arrow going in and one arrow going out. This has two arrows going out, so it cannot be the correct interaction. Another way to see this is this arrow goes to the left, so it must be the antiparticle. And it disappears and becomes a regular. And this is not annihilation. There should not be anything here after the interaction. And D, same thing. This is the antiparticle before the interaction. There's an antiparticle after the interaction. You still need the regular particle to destroy the other one, and this is not the correct interaction. Moving on to this next question, question number 24. The question reads, burning 1 liter of gasoline produces more energy than burning 1 kilogram of coal, and the density of gasoline is smaller than 1 gram per cubic centimeter. What can be deduced from this information? Before we begin, we have to define some terms. We need to know what energy density is. We have to also know the definition for specific energy. And we also have to write down the definition for just mass density. So first, energy density. The energy density of a substance is defined as the amount of energy per unit volume. On the other hand, specific energy is the amount of energy per unit mass. And finally, just regular density, which is the short form of mass density, is simply the mass over the volume. And because they all have volume mass in the terms, there's a relationship between specific energy and energy density. So let's define energy density as U sub D for density and specific energy as US. And what you have is energy density divided by the specific energy is equal to just the normal mass density, which we will call rho. So there's a way to convert one type, which is energy density, into specific energy by using the density of the substance. So second thing we have to realize is you need the specific, well, not the specific, the mass density of the substance that you're going to use. So if you want to convert the energy density of gasoline into the specific energy of gasoline, you need the density of gasoline. Likewise, if you want to do the same thing for coal, you have to have the density of coal, which we do not have. So in order to compare the energy of gasoline and coal, we have to be using the same concept. But when it says 1 liter of gasoline, it's per volume. So this is the energy density of gasoline. When it talks about 1 kilogram of coal, it is talking about the specific energy of coal. So you have to convert one of these to the other concept in order for you to be able to compare them. We do not have information about the density of coal, but we do have information about the density of gasoline. So by using this equation, the specific energy of gasoline would be equal to the energy density of gasoline divided by the density of gasoline. Now, if you look at the question, or the options for this question, it says A, energy density is greater for gasoline. Well, that would mean you would have to convert the specific energy of coal into energy density, which we are not able to because we do not know the density of coal. B, you're comparing the specific energy of gasoline and coal. This we can do. The energy density of gasoline the energy of gasoline was already greater per liter, but if you divide by the density, which is smaller than 1, it makes it the amount of energy even larger, which means that the answer should be B. The specific energy of gasoline is still greater than the specific energy of coal. In this next question, question 25, it says, which change produces the largest percentage increase in the maximum theoretical power output of a wind turbine? So you have to use the theoretical kinetic energy of wind, or the theoretical power of wind, which is 1/2 times the density of the air times the cross-sectional area of the windmill times the velocity of the wind to the power of 3, which can be found in the physics booklet. So if you look at the options, if you double the area of the blades, you would simply double the power. On the other hand, if you double the density of the fluid, you will also only double the power. If you double the radius of the blades, that would mean the area, which is proportional to the radius squared, would be 4 times greater, which means the power is 4 times greater. And last, if you double the speed of the fluid, that would mean it's 2 to the power of 3, which is 8 times the power. The answer should be D. And number 26, the question reads, which is correct for the tangential acceleration of a simple pendulum at small amplitudes? So first of all, a simple pendulum at small amplitudes is approximately the same as the motion of simple harmonic motion. And the tangential acceleration would be similar to the restoring acceleration, or the restoring force. So this acceleration should be proportional to the displacement and in the opposite direction. It cannot be A because this is inversely proportional. It is not inverse. Recall that inverse is 1 over the variable. This is just in the opposite direction. B, it is proportional, but if it does not include the concept of being in the opposite direction of the displacement. Same thing for C, it's missing 1 part. So the answer should be D, it is proportional and opposite direction to the displacement. In question number 27, the question reads, the diagram shows the diffraction pattern for light passing through a single slit. What is the wavelength of the slit divided by the width of the slit? So first, once you identify that is a single slit that's being talked about, we have one equation for single slits, and it's the angle to the first minimum is equal to the wavelength divided by the slit width. And this is exactly the ratio that we're given here. Wavelength of light divided by the width of the slit. And all we have to do now is we have to use the graph to identify the value for this angle. The value for this angle is going to be 1, and we check the units to the power of 10 to the negative 2. So this is 1 times 10 to the negative 2 radians. And because of that, the answer should be A. Question number 26, the question reads, light is incident on the diffraction grating. The wavelength lines 600.0 nanometers and 601.5 nanometers are just resolved in the second order spectrum. How many slits of the diffraction grating are illuminated? So the equation for resolvance, or resolving power, is the order, the number of slits being illuminated, and it's equal to the average wavelength divided by the minimum difference. In this case, the order is 2 because it's the second order. The average wavelength will be 600. And if you were wondering why not use the other one or use the actual average, the difference between 600 and 601 is so small, it would not really make a difference in the answer. So if you're just estimating, the round number is better. And you divide by 1.5 nanometers, which is the smallest difference that has to be resolved. N is simply 600 divided by 3, which is 200. The answer should be C. Question number 29. On approaching a stationary observer, a train sounds its horn and decelerates at a constant rate. At time t, the train passes the observer and continues to decelerate at the same rate. Which diagram shows the variation with time of the frequency of the sound measured by the observer? So first, the train is the source. At first, the source and the observer are moving towards each other, so the frequency should be higher. So if you look at the options, initially all the frequencies are higher than the horn's actual frequency. But number two, the difference in the frequencies depends on the velocity. If the train has a higher velocity, then the difference in frequencies will also be greater. But it's decelerating, so it's slowing down, and the frequency should decrease. So it cannot be A. It would not be able to be C, because these frequencies are increasing and moving away from the horn's actual frequency. The observed frequency should get closer to the actual frequency. Second, after the train passes the observer, now the source is moving away, the frequency should be lower. You can see in both cases it is indeed lower, but it's still decelerating. And the difference in frequency is still proportional to the velocity. And if the velocity goes to 0, then the difference should also get closer and closer to 0. So the answer should be D. Because eventually, when the train stops, the horn's frequency that is observed should equal the actual frequency of the horn. In this next question, number 30, the question reads, a particle with charge negative 2.5 times 10 to the negative 6 coulombs moves from point X to point Y due to a uniform electrostatic field. The diagram shows some equipotential lines of the field. What is correct about the motion of the particle from X to Y and the magnitude of the work done by the field on the particle? So first things first. Let's highlight the fact that it's a uniform electrostatic field. That just means the electric field does not change and is always the same. And the reason that is important is that the electrostatic field is defined as the force per unit charge, which means that the force on the particle is equal to the charge times the electric field. And because the charge of the particle doesn't change and the field doesn't change, the force also does not change. Which also means the acceleration also does not change, meaning the force and acceleration are constant. If you look at the options, the only two options is uniform and linear motion, which means constant velocity. Incorrect. It is in fact accelerating. So the answer must be either C or D. It's uniformly accelerated. Number two, we can calculate the amount of work being done. The work done is equal to the charge times the change in the voltage. In this case, the charge is given to be negative 2.5 times 10 to the negative 6 coulombs. And you will multiply this by the actual differences in the voltages, which would be final 700 kilovolts minus 300 kilovolts. If you actually do the calculation, you would get about negative 1 joules. So the answer should be either B or D. The easy way to kind of solve this problem as well is if you multiply these two numbers, as long as it's moving to another of the lines, it would not be able to be 0. Second, if you're confused about the signs, the only reason there's a negative sign here is because this work done is the work done on the particle. And in the question, they asked for the work done by the field, which would be the opposite direction, so it's the opposite sign. In question number 31, the question asks, which is a correct unit for gravitational potential? We will start by writing down the definition of gravitational potential, which is gravitational potential energy divided by the mass. And this would be joules per kilogram. Immediately we can eliminate B because it's kilogram to power -1. And we break down joules into more simpler units. We use the equation for force, for work, which is force times displacement. So joules is the same thing as newtons times meters. That also eliminates option D because it's multiplied by meters, not divided by meters. Now we break down newtons into more basic SI units, which would be kilograms times meters per second squared, multiplied by meters divided by kilograms. The kilograms cancel out. Meters times meters is meters squared, divided by second squared. The answer should be A. Next, question number 32. A planet has radius r. The escape speed from the surface of the planet is v. At what distance from the surface of the planet is the orbital speed 0.5 v? So, if you go to chapter 10 in the physics booklets, you will find both the equation for the escape velocity, which is the square root of 2gm over r, as well as the equation for the orbital velocity, which is the square root of gm over r. But here's the thing. We will use capital R as the radius of the planet, and now we have to use a different unit for the orbital distance, because if you recall, this is going to be at a different distance from just the radius of the planet. So I'm just going to insert x as a value for now. Finally, it says you want an orbital velocity that is 1/2 the orbital speed. Let's make this equal to 1/2 square root 2gm over r. And if you simplify this, you'll get that the orbital distance is just 2r. But 2r is not the answer. And the reason it's not the answer is because they did not ask for the orbital distance, they asked for the distance from the surface of the planet. And if you're confused about why that is a different value, this would be the orbital distance from center to center. The orbital height from the surface of the planet is only from here to here. So you have to subtract 1r from the orbital distance. 2r minus 1r is just r, and the answer should be B. In this next question, number 33, it says a conducting ring encloses an area of 2 square centimeters and is perpendicular to a magnetic field of strength 5 milliteslas. The direction of the magnetic field is reversed in a time of 4 seconds. What is the induced EMF in average in the ring? So first we'll start by using Faraday's law, which allows us to calculate the EMF in the ring, which is negative n, which is number of turns, times the rate of change of flux. We have to see that the n is going to equal to 1, because it's just one ring, it's one loop. And we also have to calculate the change in flux. The change in flux is equal to the final flux minus the initial flux. Flux is equal to the magnetic field strength times the area. So the initial flux is the 2 centimeters, which we will write as 2 times 10 to the negative 4 square meters. Next, you multiply by the magnetic field, which is 5 milliteslas, which is 5 times 10 to the negative 3 teslas. What is the difference between the initial flux and the final flux? The final flux is in the opposite direction, so we also have the opposite sign. Instead of being positive 5 milliteslas, it will be negative 5 milliteslas. That would be 2 times negative 5 And I would just put all the powers of 10 together, times 10 to the negative 7. So this would be negative 10 minus negative 10, be negative 20, times 10 to the negative 7. And I could simplify, but it doesn't really matter at this point. We just simplify at the end. So you have negative 1 times negative 20 times 10 to the negative 7 divided by the time of 4 seconds. 20 divided by 4 is simply 5 times 10 to the negative 7. And the answers are in microvolts. So this would be 0.5 microvolts. The answer is D. Number 34, the conservation of which quantity explains Lenz's law? Lenz's law is related to the conservation of energy. So immediately you can just go down to B. And the reason this is related to Lenz's law is Lenz's law gives us directions of current, directions of induced magnetic fields, and the directions of the force. And in these three directions are always such that if there's a conductor that is moving, let's assume this conductor is moving towards the right with a velocity v. The kinetic energy has to go down in order for it to be converted into electrical energy. To reduce the kinetic energy, you need a force in the opposite direction. So Lenz's law makes sure that this force always is in the direction such that it reduces the kinetic energy, and that kinetic energy is converted into electrical energy, which is the concept of conservation of energy. Number 35. A resistor designed for use in a direct current is labeled 50 watts and 2 ohms. The resistor is connected in series with an alternating current power supply of peak potential difference 10 volts. What is the average power dissipated by the resistor in the AC circuit? So first, the peak voltage is 10 volts. We can use this to find the peak current, which is the peak voltage divided by the resistance. 10 divided by 2 is simply 5 amperes. And if you multiply the peak voltage and the peak current, you'll get the peak power, which is 50 watts. This is not the question. The question asks for the average power. The average power is 1/2 of the peak. Which is 1/2 of 50, which is 25. The answer is A. Number 36, it says a capacitor of capacitance X is connected to a power supply of voltage V. At time t equals 0, the capacitor is disconnected from the power supply and discharged the resistor of resistance R. What is the variation of the charge on the capacitor? If it's a discharge, we have the equation for the charge left over, Q, which is the initial charge, Q0, multiplied by E to the power of negative t over the time constant. The time constant is, of course, resistance times capacitance. In this question, though, capacitance is represented by the letter or variable x. So we just replace the C with x, like so. Next, if you look at the possible answers, we can eliminate the first one because it's not what we have here. You're supposed to be dividing by RC or RX. B is a probable answer. It cannot be C either. It can also probably be D if you just look only at the exponents. Next, the difference between B and D is this factor for the initial charge. You take the definition of capacitance as the charge per unit voltage, which makes charge equals to the capacitance times the voltage. In this case, they're using X as the capacitance, so it's XV. The answer is D. Number 37. What is a consequence of the uncertainty principle? A. The absorption spectrum of hydrogen atoms is discrete. This is not a consequence of the uncertainty principle. This is the quantization of angular velocity, or the energy levels of the electron. So it's not A. B. Electrons in lower energy states have short lifetimes. This is incorrect. An electron in its ground state is stable, so it has a very long lifetime. It would not decay from there. C. Electrons cannot exist within nuclei. This is actually the answer. The reason for this is it's really, really hard to confine the electron inside a very small space. This is from the example of the electron in the box. If you try to confine an electron in a small space, the electron would have to have more momentum uncertainty, which gives it more probable kinetic energy. So if you try to put an electron inside a nucleus, the nucleus is so small, the electron would have to have a very, very large amount of kinetic energy, which is not possible. And D, photons do not have momentum. Photons do have momentum, so it is also not D. Number 38. In a photoelectric effect experiment, a beam of light is incident on a metallic surface W in a vacuum. The graph shows how the current I varies with the potential difference V when three different beams X, Y, and Z are incident on W at different times. So we have the graph here. First things first, what changes in this experiment is the beam. So what we could change is you can change the frequency, so they can have different frequencies. Or they can have different intensities. So let's look at the options. 1. X and Y have the same frequency. X and Y, if they have the same frequency, they would also have the same stopping voltage. And they have different stopping voltages, so they do not have the same frequency. So number 1 is incorrect. Number 2, Y and Z have a different intensity. Y and Z have the same stopping voltage, which means they have the same frequency. So the only reason they will have different slopes is they have different intensities. And remember, the intensity determines the number of photons there is per unit area and unit time. So if you have higher intensity, you have more photons. Every photon could conceivably release one electron. So if you have higher intensity, you also have more electrons, which means there's a higher amount of current. So number 2 is correct. Number 3, Y and Z have the same frequency. Y and Z, they do indeed have the same frequency because they have the same stopping voltage. Number 3 is correct. So if they ask which statements are correct, only 2 and 3 are correct, so the answer is C. In this next part, number 39, it says the graphs show the variation with time of the activity and the number of remaining nuclei for a sample of radioactive nuclide. So the first graph is activity versus time. The second graph is the number of remaining nuclei versus time. The question asks, what is the decay constant of the nuclide? So you could conceivably get the decay constant by using the half-life. But the issue is this is a multiple choice question. You do not have access to a calculator. So what you should do, since you have information about the activity and the number of nuclei, we use the equation for activity as being equal to the decay constant multiplied by the number of nuclides. We take a single point. The initial point is easier to use. we use 0.7 times 10 to the 6th for the activity. You can use 1 times 10 to the 6th for the number of nuclides, which means the decay constant would simply be A, 0.7 per second. And 40, what is a reason to postulate the existence of neutrinos? Neutrinos were postulated because of the continuous nature of the beta particle kinetic energies. So the answer is D. And the reason they postulated the existence of neutrinos because of this is that the amount of energy released during this reaction should have been discrete because of the nuclear energy levels. So they expected all the beta particles to have the same energy every single time. The reason they don't have the same amount of energy is because part of the energy is shared with a neutrino. The amount of energy each has depends on the initial momentum of the particle, which is more or less random. And because of this, it feels as if the energy of the beta particle is any value between 0 and the maximum, which is more or less continuous as well. A, let's look at the other options. Nuclear energy levels had a continuous spectrum. This is, of course, incorrect. Just like electron energy levels, they are not continuous, they're discrete. B, the photon emission spectrum only contains specific wavelengths. This proves electron energy levels again. And C, some particles are indistinguishable from their antiparticle. This is also not the reason why the neutrinos were postulated. So the answer has to be D. Well, that's all for today. Thank you for watching and see you next time.